One good afternoon. My name is Alex Schneider. I'm a field application at Würth Elektronik and I will be your host today. Welcome back to the fourth edition of the Analog Würth Elektronik webinar. And today we have a topic about isolated power. I think a very interesting topic, also something that a lot of people have questions about and still maybe even struggle sometimes with. So we have invited two engineers to talk about that topic, one side from the IC point of view, other side from the transformer point of view. That being said, Ernest Bron from Analog Devices will start off this meeting with his presentation, and Thomas O'Brien from Würth Elektronik, who is a design engineer based in Munich, I think, will do the second part of this webinar. During the webinar, we have you all on mute, but you can ask us questions. We have on the right side options to ask questions in the Q&A section of the tool. Sometimes it's called a little bit differently because of language settings, but there you can write down all your questions you have on both of the presentations. At the end of the session, which will take about approximately 60 minutes, we will have a Q&A sessions for about 10-15 minutes, or maybe a little bit more if there are a lot of questions. If you have any issues, try to contact us. This session is being recorded. We post this always on our YouTube channel, which you can find on YouTube, of course, and also on our own website. This will take roughly a week to get there, so please don't ask me for when I can have it. It will take a little bit of time because we need to do some video processing there. So that is what we're going to do today. I hope you all have a good webinar. Again, if you have any questions during this session, please feel free to ask them. And I will hand over control to Ernest Bron to start his presentation.
Okay, you can see my screen, I hope.
We can, and we can hear you.
Okay.
Good luck.
All right, thank you. Welcome. So for the, I think fourth and last session that we are going to do of this series, I guess, isolated power, mostly about flyback. It's only 30 minutes, so it will be fast. I hope not too fast, but basically the idea is to give you a rough, quick idea of how flyback converter design has evolved and how simple it is these days, actually. All right, so topics for today: introduction to isolated power as a whole, right? Not just purely flyback, but then we will focus mostly on flyback because, well, it's only so much we can do, and actually flyback is the most common one seen, at least I see it at our customers. We'll talk a little bit about why, how, some trends, the procedure, general procedure, how to do it, and then a very small portion about operation and simulation, just to show that you can use actually LTSpice to operate or to evaluate operation of a flyback converter, which I find very, very helpful because it allows you to much better understand what you're doing before you actually go and build hardware. All right, isolated power, why and what? So why would you need isolated power? Well, the most obvious answer is because your marketing guy says you need to do it, but okay. Essentially, you would want to consider an isolated supply if you need isolation, right? If you want to break the ground loop, or if you want to isolate the load from a high voltage input. But very often also you want to use isolated supplies because you want to use the transformer to be able to do high step up or step down applications. You want to use the winding ratio to get your duty cycle of your controller into a more usable form, right? If you do a simple step down, a buck converter, 100 to 1 is very difficult to do. It's a 1% duty cycle, and but if you want to do that in in a flyback with a suitable winding ratio, it might be much easier to achieve. Also with flybacks or other isolated topologies, you can quite easily do negative to positive or positive to negative applications. You can do relatively easily multiple output voltages. It does have some side effects. I'll talk about it a bit later, but just adding windings, you can generate a bunch of additional voltages as well, just using one controller. So topologies, there's a bunch of topologies. This is by no means everything, but in general, these are the ones we see. So first of all, the flyback, right? Then you have a forward, you have an active clamp forward, you have a 2-switch forward, a push-pull, and a full bridge converter. This one you see quite a bit as well. But there's a lot of topologies, and how do you decide which one to use? That's always the main question. So in yellow, I mark the power, because typically that's the one thing that people initially look at, right? If your power is more than 60 watts, then typically a flyback is a no-go, and you would have to go to something else, like push-pull or half-bridge. But each of the topologies also has other side effects, or let's just say advantages or disadvantages, right? For the flyback, the advantage is it's really simple. There's tons and tons of devices on the market, but it's compared to anything else, it's simple. It just has one switch and typically one output rectifier diode. You can make it more complex by making it synchronous, but okay, we'll get to that. A big downside of flyback is that you have quite a bit of ripple current through the output capacitor. But it can do easily high step up or step down. So you can do very high output voltage, or you can go from very high input voltage to relatively low output voltage. And if you use a non-synchronous, then typically you would be limited to about 5 amps, because then the diode starts, taking up too much heat. More than 5 amp to a diode is really wasting a lot of power, generating a lot of heat. Then you'd need to go to do a synchronous rectification, which makes the whole thing a lot more complicated, and it starts to look much more like all the other topologies, which have many more switches inside. So to repeat, generally people just look at the power level. If you are below 60 watts, then flyback is the way to go, typically. So flyback, comparing it against a buck and a single transistor forward regulator, one of the things you need to realize, a flyback is good in efficiency, but it will never be as good as a buck or the forward regulator. It's just not going to happen. You can make it again synchronous and it'll be a little bit better, but if you just use a standard topology, which is what we see mostly, then you're talking about 85, 86 efficiency at most. Something to at least keep in mind. So how does it work? Very briefly, so you have your transformer, right? There's, let's say, 2 phases, T1 and T2. During T1, current goes from the input through the transformer, the switch is on, right? So energy is being stored in the transformer. And then in T2, the switch turns off, the energy is released, the diode becomes forward biased. Now the current is applied to the output, but also recharges the cap. And by the way, during T1, there is really no energy transfer, so all of the power is being provided. All the power that's needed on the output is being provided by the output capacitor. So that's inherently the basic operation of the flyback. Now, looking at the basic structure of how you would want to build a flyback, and this is a couple of years ago. You see a lot of components, right? You see your controller, you see your external FET, it's maybe integrated or not. Then you see a transformer, you see your output circuit where you have a reference, secondary side reference, and some compensation. All of that is then going back to the forward through some isolation, Opto in this case, and then going back to the controller to close the loop. And then you might have some snubber circuitry to get rid of the spikes and noise on the primary side. So all of this looks complicated, right? This is one of the reasons why people were always shying away from doing flybacks, because it's so much more complicated than just doing a silly buck converter. And actually, a lot of this has been made a lot simpler, right? So the traditional approach that I just showed, right? We have the controller, we have the transformer, the reference and compensation on the isolated side, going through the isolation back to the controller. After this, people come up with this idea to use a secondary winding on the or third winding on the front side, feed that into the controller and use that to regulate the output. So now no more opto and no more secondary side reference. Everything is on the front side. Makes it already a lot simpler, a lot potentially lower cost. But it does have a side effect of load regulation is not that great. So as you start varying the load on the output current, the output voltage will vary quite a bit, typically about plus minus 7%, which may or may not be a problem. It's definitely not as good as if you would use something like this and you design it well. You get really good load regulation. So after this, people come up with what we call the no opto flyback. This is one example here, and you can easily see it's simple, right? There's no more opto, there's no third winding. It's just a controller, it's a transformer, some snubber, and that's it. Much simpler. And the load regulation actually is also good. So this is pretty much the topology of choice for most of the converters we see today being built. So how does it look like? Let me just get rid of the animation. So this is showing the simplest form, right? So I take it as an example, a very simple controller, or actually a converter with a switch inside. It's very few pins, and this is a no opto flyback in its simplest form. And you can see it is simple, right? This is the IC. It's just a cap here, the transformer, and then on the output you have another cap and actually a zener, and that's it. So transformer, no third winding, no opto, a single resistor that sets the output voltage. There's no external compensation. It's all done internally, and there is an under voltage lockout through the enable. The simplest form of opto. So now you can see doing an isolated converter becomes a lot more simple these days. Now, how does it regulate the output voltage? Actually, so the way it works, it actually senses the voltage on between switch and VIN, because as you close the switch internally, you get the on the switch node, you get the voltage which is equal to the input voltage times the ratio times V out. Right? So by measuring this, you can actually figure out what V out is, and you can use it to regulate, to basically vary your duty cycle to control the output voltage. This is how it works. And then how do you get good load regulation? Because the latest generation devices that implement this scheme actually have very good load regulation. If you look at the actual waveform on the switch node, you can see actually a slope. It is a bit dependent on the load current. So you want to make sure you measure this voltage when the load current or the diode current is low. And the boundary mode control operation of these devices ensures that we get this good load regulation, because we always measure it at the zero crossing of the current. And that's when you get the best measurement, and that's how you can achieve a very good load regulation of plus minus 1%. So now that we've basically thrown away all the old flybacks and say, okay, if you want to do a flyback now, use this new methodology. The question is then, how do you design it, right? And the nice thing about these new parts is the design procedure actually is a lot simpler as well, because a lot of the all the whole secondary side with the the TL431 and whatever on the secondary side is all gone now, and we really don't need to worry about all of that anymore. So the easiest way to do this, and actually I think the bulk of our customers use this, they will go and there's tables in the data sheet that say, okay, you want to do something, this is your input voltage range, you have something in the middle, let's say you have something at I don't know, 30 volts and you want a 15 volt 1 amp output, then you can use this this transformer. It has these parameters, and but basically you can just use this and it will work. But it's key to remember that you don't need to use this, right? You can actually go and modify it as you want. You can use another transformer if you want, because maybe you don't want this, but you want a smaller one, and you make the trade-off because now it has a slightly different inductance and stuff like that. So you need to start thinking about how to actually calculate the whole thing, and we'll get into that. But basically, the first step is always use the table, and a lot of people will use that. But if there is other criteria, then of course you need to start looking at, okay, what can I do to optimize this? So then the procedure becomes as per data sheet, and I'll go over it in, I think, 3 or 4 steps here. The generic procedure, right? So the first thing typically you do when you, again, I get rid of the animation. The first thing you typically want to do when you design something, if you use a converter that has an internal switch like this one, you look at the maximum voltage the switch can take. In this particular case, 65 volts, right? And then, because you know how flybacks work, you say, okay, this is my maximum input voltage. I will see that on the switch. But as I turn off the switch, I get a reflected voltage back. And the reflected voltage roughly is the winding ratio times the output voltage. It's going to be a diode drop, etc. But you know, for simplicity, actually in the equation it's done here, but for my explanation, I'm just going to ignore it. So you have your 32 volts, and then you have a winding ratio times 5 volts. So if you would have a winding ratio of 5, right, then you have 25 volts being reflected back. So you have 32 plus 25. You're already at 57, right? So that's the quick and dirty way I always check it. In reality, I need to take into account the VF. And then you also need to take into account the leakage inductance of this, which will cause all kinds of ringing and spikes, which are going to be potentially a problem, which is also the reason why you always have this snubber here. But anyway, the equations will get you a certain winding ratio that you can tolerate to not exceed this 65 volts, 3.4 here, right? So you would use a ratio of about 3. So that's step 1. Select the turn ratio. Then this turn ratio will determine the maximum output power. So again, here's a bunch of equations that will help you determine the maximum output power you can get at the minimum input voltage. But typically in the data sheets, you will also find these curves that will show you, okay, for a given input voltage, you can get this output voltage for a given winding ratio. So based on this, you can also quickly then determine, okay, a 3-to-1 at I don't know, 30 something volts, I can get 15.4. But if my input voltage drops to, I don't know, 10, I can get maybe 8 watts, right? So then you can determine whether or not you can achieve the output power that you need for your application. Right, and if you cannot, then you must use a different winding ratio, and if you cannot do that, you might have to go to a different controller or a different flyback device that can do more power, that has a higher power switch or potentially a higher voltage switch, or use a controller with an external switch that you can define as you see fit. Once we have that, you can then go and look at the inductance, right? So every transformer would have a certain winding ratio, but also have a certain inductance, right? And the inductance has a limit. It needs to be higher than a certain value, which is based on an equation. And the equation is based around 2 datasheet specs, which are the minimum off time, right? So as the switch turns off, we sample at some point the switch voltage. And we do that after a minimum time of 450 nanoseconds for this particular device. So every device will be different, but every device by itself will have a minimum off time. You need to wait, of course, for all the all the crap to go away and then become nice and quiet, and then that's when you sample, and that's the minimum off time. So that's a specification that is part of the equation that determines the minimum inductance. And likewise, there's going to be a minimum current which will also have an effect on the minimum inductance. So you look at the waveforms here, and then you can see if the switch, if the off time for the minimum off time, you can see the limits here, and based on that, you will have a minimum inductance. So now you have your transformer winding ratio, and you have your inductance. And then you need to look also typically at the saturation, right? So then you start calculating the duty cycle. These are just the generic equations for DCM Flyback converters. So you have your duty cycle based on the input voltage, output voltage, and winding ratio. Out of that, you can get the current to the switch and the switching frequency, right? And the current to the switch, you determine it for the worst case scenario to get the worst case current, and then you want to make sure your transformer is not going to saturate for that current with a decent enough margin. Or once you've done all of that, you find out there's Excel spreadsheets that can do that for you. So that's of course a secondary, the alternative approach. The only thing is when you do this, of course, you need to know what you're doing. Make sure you make the right trade-offs. But these things are available, and you can have a look at more quickly optimizing the design you need. I need to speed up, I guess. So commonly designed topics once you have a design. So one of the more common things we see is things like cross-regulation. So people make a flyback because of the ability to do multiple rails into one design. Right? You see the principle here. We have one controller. We have output 2. We have the feedback here of the Opto. So this is actually still an old principle. But then the secondary winding on the output will generate Vout1. It's not regulated, right? So Vout1 would have what we call cross-regulation issues. So it would vary over load, and you would not have a good enough, potentially not have a good enough regulation on Vout1. This cross-regulation really depends on the non-ideality factor of the transformer and the diode. If they were ideal, you would not have the issue. But if they were ideal, we would all not have a job. So you have this problem. The question is it bad or is it good? So in terms of the no Opto flybacks, typically how you would deal with this, you would take the higher current rail, and that's the one it regulates to. The other ones are basically open-ended or not regulated back. In this case, you get reasonably good cross-regulation, and the cross-regulation arrow can only be positive. Some waveforms here. We see 2 on the left. We see the blue one is the one that's being regulated, Vout1, and we sweep the output current from 0 to, or very low, not 0, to something higher, right? 60 milliamps. The other ones are all regulated or loaded very lightly at 0.1 milliamp, and we see that as we increase the current, you see the output voltages of all the other 3 rails are going up, but they're only going up, right? So this is good or bad. It's bad, but is it bad enough for you to need some post-regulation LDO or not? That depends on your design. But it only goes up. That's really important, because in many cases you would really hate it if it goes down, because then you might not have enough headroom for your circuit, right? If it only goes up, you can probably clean it up with some LDO or post-regulation. If the output's the one that we're sweeping is actually heavily loaded, you can see that the cross-regulation is a lot better. But again, it will not go down. Okay. The other thing we often see, or often question we get, is we need the isolation, but we can't use the transformer. It's too big, it's too bulky, it's too expensive, whatever the reason you come up with. Or maybe you don't need it, you just need some functional isolation. In that case, you can actually also use a coupled inductor. In all honesty, the efficiency is not going to be great, but it's going to be small, it's going to be simple, and certainly if it's just functional isolation you need, in many cases using just a coupled inductor will be enough. You need to look at the leakage. Leakage should not be too high, especially with coupled inductors. The leakage might be high because in many cases people use coupled inductors for septic type of topologies in there, you want quite a bit of leakage actually. So in many cases, the parts you're looking at might not be optimized, but there are certainly devices out there that you can use. Then if you do the other thing, right, if you do a very high output voltage, so this is the case where you might actually not need the isolation, but just need the very high duty cycle type of application. So in this particular case, right, we have a 250 volt output out of a worst case 18 volt input. The transformer then has a very high ratio, 1:10, right? So that in order to get the output voltage and not have a ridiculously small duty cycle. So now you look at the reflection, the voltage reflection back on the switch, right? So we have worst case 32 volts on the input from the input. So this is 32 volts plus the reflected output voltage, which is 250 volts, a ratio of 10. So we get 25 volts coming up. So we have 57. That's okay. This is a 65 volt part. So you should be okay. But the other side effect you get if you do this, you get the reflected capacitance also on the switch, right? So you have an output capacitance, which tends to be big because of inherent nature of a flyback to get rid of the ripple. And then you also have the capacitance, the parasitic capacitance, if you will, of the transformer. You add that up, it's reflected back to the switch node, but it's reflected by the ratio squared. So we get 100 times that capacitance back on the switch node, and that switch node might not like that. It needs to suck up all this capacitance. So the switching edge will be probably slow. So there is a common way around this. Basically, you split the secondary winding. So we still have the same output voltage this way. We have two caps now, two output caps, two diodes. You still get the same reflected voltage on the switch node. You see the calculations here. I won't go into details, but it's still 57 volts. But now the capacitance that's being reflected back is only half. Right? It's 5 squared plus 5 squared times capacitance. So it adds up to 2 times 25, which is 50 in this case. So it's a common trick to help get rid of too much reflected capacitance on the switch node. Operation and simulation. The one thing I keep telling everybody is use the LTSpice. It's the models that we have for most of our converters are pretty good, and one of the really nice things, a solution in LTSpice that works fine is by no means guaranteed to work in a real live design, because there's really tons and tons of things you can do wrong on your layout, etc., etc. But it allows you for a very good starting point to really understand what the part is doing and how it's behaving, and how the use of different transformers are going to give you a different type of behavior and how you can make the trade-offs. Models are available for most of the parts, but also for the different parts we have, apart from the standard jigs, we have these demo circuits that are typically copies of the eval boards that we provide. So you can, in many cases, get a LTSpice circuit for the demo circuit of the actual board that you might get if you order an eval board from us as well. And then these models typically contain the transformers that are modeled as the transformers that are used on the actual board. Very often they don't contain the actual model from Würth. I know Würth has tons and tons of models that can be used in LTSpice, and potentially they would have a model for this one as well. But then you need to import their models and get them in there as well. And then you can run the simulation, and this actually, I'm not running it live here, of course, because I don't have time for it, but this doesn't take so much time, and you actually see the output voltage ramping up slowly. And one of the really nice things about this is you can then put potentially your post regulation or whatever you want to put on the other side, you put that in the circuit as well. And so you get a really good live behavior of the device as it performs. And I think I am at the end of my talk. Almost. Okay. Okay. So we zoom in. You see here the leakage voltage, the spikes, right? And you potentially put some additional snubbers to get rid of it. and you see your reflected voltage on your switch node. And now I'm at the end. So I hope it was clear. There's not a lot of details. I do apologize for it, but it's only 30 minutes. But again, the point was to show you how easy it is these days to make flybacks if you really need to go and make one. And I can only ask you again that if you have questions, if you need support, samples or whatever, please have a look at my email, drop me an email, and we will try to help you. Thank you, and back to you, Alex.
Thank you very much for your very interesting story. Any questions, of course, are welcome. Please leave them in the Q&A. I already see something coming in, but we go to that later on. Just to add on to your presentation a little bit, you talked about the use of coupled inductors. We can do that ourselves as well, because we have, of course, coupled inductors in our portfolio. We also have them for this type of application. So they specifically designed them for being used as a transformer, not so much for a step converter. Of course, a wheel transformer is better, but it's still there. And just to give you an idea, maybe I can share this quickly. If you look at our portfolio, it's quite big, but we have this MTCI version, which is a multi-turn version, which can go up to 1 to 3 turns ratio, which has an isolation of 800 kilovolt, 800 volts, sorry, don't overdo. Functional isolation, of course. We also have versions that can do up to 2 kilovolts of isolations, which are meant for this kind of operation. But that's just additional information. So thank you again, Thomas. I hope you are ready, because I'm going to make you a presenter. So you should be able to start your presentation right now. So up to you, Thomas.
Yep, okay. Yeah, hi, sorry about the technical issues there. My name is Tomas O'Brien, and I'm a design engineer with Midcom Europe, based in Munich here. Before that, I was working for 15 years in power supply development back in Ireland for a company called Traco Power. And so I have a little bit of experience with power supplies. So today we're going to talk about flyback transformers, obviously. Sorry, Alex, how do I go to the next? Oh, take control. To the next slide. Okay, yeah, so we're going to look today at discontinuous flybacks. Then we'll have a quick look at whether we want to pick a custom or a standard transformer. We'll do a quick review of the BH curve, and then we'll take a closer look at the things we need to look out for when we pick a flyback transformer. And then if we have time, we can look a little bit at the parasitics for our transformer. So DCM flyback transformer. Well, why do I have transformer in inverted commas here? Basically, flyback transformer is a coupled inductor. It's not a real transformer. In a real transformer, we want to transfer energy directly to the secondary when the switch is on, and so it doesn't need to store any energy. But in a flyback transformer, we want to store energy in the primary, and so it's basically an inductor with a few extra turns added on that are isolated, and this is why it's truly a coupled inductor. Another reason why we look at discontinuous flybacks only, the discontinuous flyback requires much lower inductance, and so the transformers tend to be much smaller. They're easier to stabilize. The right-hand plane 0, like the continuous induction mode flyback. And there's a lot of advanced controller ICs with the likes of valley switching and quasi-resonant switching, which really improve efficiency because they switch at much lower voltage than the old converters. And we don't have much time, so the discontinuous flyback is much more popular and much more common, and so I think it makes sense to focus on that. So why would we pick a standard or a custom transformer? Well, I guess the best approach is to pick a standard transformer and then design your flyback power supply around that. If you can, but of course most engineers end up or will design their power supply first and then end up looking for a transformer that can work. And we'll look a little bit in the details today about how to pick that transformer. And then if you can't find an off-the-shelf transformer, you'd probably have to go for a custom, and this would happen when you have special safety standards or mechanical constraints, or you have lots of different output voltages. It might be difficult to find something that can actually work. And of course, if you have a very high volume, then it makes sense to go for a custom anyway, because we can optimize it for performance and cost as well. So the BH curve is really the key to understanding how magnetics work. And the important thing to realize about the flyback and also forward is it's a unipolar topology. And what does this mean? A unipolar means that the BH curve can only work in this positive region here. So we have our H, which is magnetic field strength, and this is directly proportional to the current in the transformer. So we have H equals NP over LE times the current. And the NP is the number of turns in the primary, the LE is the magnetic path length, so this length here that we see in blue. And these two are constant. The current increases, and so the H increases. So if we look at this current here on the right-hand side, rises from 0 to an I peak, and that I peak will be determined by whatever max flux density we set for the transformer, and that's typically about 80% of the saturation current. So that's when the switch is on, current rises linearly to this point, then we switch the switch off. The current transfers instantaneously to secondary, and then it starts to drop down, as we see on the right-hand side. That means the H field goes back to 0, and the flux follows this blue path around the loop. So we can see we're only utilizing a very small portion of the max flux swing with the flyback transformer, because it is unipolar. So the current never goes 0, so we can, or goes below, never goes negative, so we can never use this bottom portion. And that's the main reason why flybacks and forwards or any unipolar topology is limited with the power. Then do we add an air gap? Well, the air gap flattens this BH curve. So the Bmax, or the saturation, stays the same, it doesn't change, but if we look here on the left-hand bottom corner, we can see the H can be much larger, and so we can increase our I peak current and hence store much more energy then in the transformer. Okay, and the next slide. So here we have a typical data sheet. This is actually a data sheet for analog devices evaluation board that we developed with analog devices, and it's for one of their isolated synchronous flyback controller ICs. And typical data sheet will have the mechanical dimensions of the transformer. It has a schematic diagram which includes the input voltage ratings and then the output current and voltage ratings. And on the right hand side we have all the electrical parameters, and if there is some safety information as well, that'll be down there. And all these electrical parameters, we need to look at these in a little bit more detail to see if that transformer can work for our power supply. So the next slide. And see if this transformer can work for our power supply that we want to design. So the first thing, and one of the most important things to decide at the start is safety compatible. Now, often they that you look at this at the start and try and figure out what you really need for safety. If you need a reinforced transformer or basic isolation, what working voltages, pollution degree and over voltage category, these all need to be determined at the start. And can pick, Würth has many transformers with different safety standards with typical values for safety that they already sell off-the-shelf transformers, so you can actually pick several transformers that already have safety built in. Then once you've established whether you need a safe or you just need a functional isolated transformer, the next thing to look at is whether we can get enough power out of the transformer. And this is pretty easy to work out. We just look at all the output voltages and currents, multiply the current and the voltage to get the power for each winding, add them all up, and then we come up with a result. So for this particular transformer, we can get a maximum output power of 15 watts. And so there's a good possibility that this transformer can work for power that needs 15 watts. But we still have some other things to look at, specifically the output currents. We might want to use all the windings, but we need to use some section of windings. And here we can see we can get 200 milliamps from the 15 volt, 500 from the 5 volt, and then 400 milliamps from the 24 volt. But hidden away in this detail, if we look carefully, 5 volt, it actually is in 24 volts, so it needs to carry the current for both of those outputs. And so the 5 output is actually capable of carrying 900 milliamps, which is quite a lot, and we could end up using that for 900 milliamps. And then the next thing we need to look at is, have we got a chance to meet the voltage we need? And with 3 outputs like this, we have several combinations of voltages that we can achieve. You see, we can obviously pick the 15, 5 or 24 that are listed on the data sheet, but we could also tie some pins on the PCB, tie all of them together. We actually get 39 volts. The only thing we need to be cautious of is we need to look at the minimum current for any winding in series. And so if we do want to use this for a 39 volt output, then we need to be aware that the minimum voltage or minimum current will be this 200 milliamps when we tie it up, because this is in series with the others. So it needs to be able to carry that current. The voltages listed on the datasheet are only a rough guide, because the turns ratio on the duty cycle will actually determine what we really get on the output voltages. But if we can pick a voltage similar, then there's a good chance it will work for us. Next thing we need to look at is the saturation current. This is a pretty simple formula to work out our peak current. And we need to ensure that the peak current will be lower than the saturation current of the transformer. So the equation is simple. Our peak is 2 times the input power, and the input power will be 15 or 20% less or more than the output power because of efficiency losses. We would know our V and min, and we typically set our Dmax to about 50%. So these are, this is for the worst case conditions in the transformer, which will be V and min, and Dmax will be, the duty cycle will always be a max at the minimum input voltage, and we calculate this for full load. And so this gives us the peak current very simply, and we can check then if that peak current is below the 2.8 amps. Nice to have a little bit more margin than that, but then we can move on to the next stage. So, and then for discontinuous conduction mode inductor, the inductance requirement is actually a maximum inductance. So if we go above this inductor, or if we have an inductance transformer above this max value, then the transfer or the operation will go into continuous conduction mode. So the current doesn't drop to zero, and then we have a different problem because we need to have a control loop to stabilize that continuous conduction mode. So we want to avoid that, and so we need to have we need to pick a transformer with a maximum inductance. Again, this is quite a simple formula. The one on the left, that these two formulas are equivalent, but the one on the left is a little bit easier. We know our V in again. This is again for the minimum V in. The T on is the on time, or the max on time for the MOSFET. Again, is at the minimum input voltage. If we have set our duty cycle to 50% and we know the switching frequency from the IC, or we can sometimes set the switching frequency ourselves, then we can easily calculate this T on. And the I peak, we've already calculated in the last step. So then we end up with an L max, and we need to pick a transformer with inductance lower than this L max. It's okay to go lower with the inductance, but the peak currents will increase. And for some, as Ernest mentioned, for some ICs, there is a minimum inductance as well, because you need a certain dead time. But the L max is the important thing to stay in discontinuous mode. Okay. The next slide. And so the next thing to check, and the last thing, is the turns ratio. And again, this is a max value, so we need to stay below a certain value, or for the duty cycle that we have picked as the max. So we had picked our 0.5 or 50% duty cycle. And if we go above that, then the duty cycle will increase. It's okay to have a higher duty cycle if your IC allows it, but the peak currents again will get a little bit bigger, and so we just need to be a little bit careful. And if we do change our duty cycle, then we need to go back to the previous steps and change that duty cycle in those. Again, calculated, this is calculated at the minimum input voltage, and we generally calculate this to the output with the lowest voltage. One other thing to check, it's just to be sure, is that the drain to source voltage, reflected voltage on the MOSFET, is not too high. And this, as Ernest already showed us, is the input voltage plus the turns ratio times V out, the V out max. And so we just calculate that, and we check that that's not higher than the voltage breakdown on the MOSFET. This is the voltage without leakage included, so we also need to include the leakage. We have a snubber there which will dampen that, but we generally need a minimum of 80% margin, or 100% margin, so we shouldn't be above 80% of the breakdown voltage of the MOSFET. Of course, if we have a separate MOSFET, we can increase the voltage rating on the MOSFET by picking a different one. But of course, that generally is either a higher cost or has a higher on resistance. Going lower with the turns ratio is okay as well, but generally requires more turns on the secondary. And the secondary, if we use an isolated wire, it can be quite bulky, and so we try to usually have as few turns on the secondary as possible to keep the size of the transformer down. Then with the transformer, every transformer unfortunately has not ideal, and we need to deal with these. So one of the first things we have is the resistance in the winding. Thicker the transformer size goes up, so we need to there's a limit on what resistance we can have, minimum resistance we can have. We also have leakage inductance, which is in series with the main inductance. Then we have capacitance from primary to secondary, called interwinding capacitance. And this is the main path for conducted emissions to flow from, EMI emissions to flow from primary to secondary. Then we also have this intra-winding capacitance, and that's the capacitance in the windings themselves. So we have that on the primary and on the secondary. And all these cause their own individual problems. And we can have a little bit of a look in more detail on the next slide. So the interwinding capacitance, that's the winding from the capacitance from within the winding itself. So from turn to turn in a winding. Yeah, that capacitance increases switching losses. So when we turn on the MOSFET, it tends to cause a big spike and some ringing, and can be detrimental for your EMI, and also causes a lot of extra losses. So we'd like to avoid that where possible. And how do we reduce it? Well, we can use thicker insulated wire, so we're effectively increasing the distance between each turn of winding, or we can spread out the windings, or if we have layers of windings, we can put some tape in between them just to, again, increase the distance slightly. And the next thing is the interwinding capacitance. As I said, this is the main path for common mode noise to get from primary to secondary, and causes EMI issues. So we'd like to have that as low as possible. The small issue with that is if we reduce that, we generally increase leakage inductance, and leakage inductance as well has its own problems. So how do we reduce interwinding capacitance? Well, we can reduce by separating primary and secondary windings as much as possible. So we can introduce some tape, or we can put in a copper shield, or even a wound shield, or sometimes just simply put in the auxiliary winding between the primary and the secondary, increases the distance and hence reduces the capacitance between them. Then the leakage inductance. The leakage inductance is basically the lines of flux that don't connect between primary and secondary, and so the further we have the secondary away from the primary, then the more lines of flux will not couple to the secondary, and so the closer they are together, then the lower the leakage. The leakage is a big problem because one, it's lost, it's waste of energy. We need a snubber to usually clamp the voltage so we don't have issues with our MOSFET down. And that snubber just wastes energy, it gets hot, and yeah, but still we need to do something about it. So ideally, it's better if we can do something about it in the transformer, so we don't have to have such big snubbers and waste so much energy. Yeah, the problem with that, as we reduce leakage, then we usually increase this interwinding capacitance, and we can have other problems with EMC. So it's a little bit of balancing all the losses. So here we have kind of a complicated equation for the leakage, but if we look at it in detail, there are two main highlights to take away. This leakage inductance is proportional to the turns squared, and also inversely proportional to the number of splits squared. And the number of splits means how often we actually split the primary winding. So if we look here at a standard winding, in the middle here we start off with our primary winding in red. This is cross section, so it's on two sides of the core, and then we put some tape and we do our secondary winding. To make a split winding, we start with half the primary, and then we wind our secondary, and then we finish off with the rest of the primary on top. So we've effectively sandwiched the primary in between two, or the secondary in between two halves of the primary. And because this is squared, reducing that, or having that extra split reduces the leakage inductance by about 75%. So it's a great way to reduce leakage inductance. Of course, it does increase this interwinding capacitance as well. So again, it's a balance. The other big way to reduce leakage inductance is to reduce the number of turns. Again, that's a squared factor. So if we reduce the number of turns by half, again, we can reduce the leakage by up to 75%. But of course, we need a minimum number of turns to give us our inductance, number one, and also to give us a saturation current rating. So there's a limit on how far we can go or reduce our turns. And so then the last thing I'll look at today is one of the tools we have in Würth Elektronik for picking a transformer. So you have one option is to go through all the equations that I gave you, or the other easier option is to go onto the Würth Elektronik website and go into Red Expert, and then they have a very nice program there to select a transformer for you. So first of all, you need to select which mode of operation you want to work in. So discontinuous mode, boundary mode, or quasi-resonant mode are the options. Select the one you desire. Then we have to fill in a few basic parameters, the input voltage range, then the output or output voltage and currents for up to 3 windings. You can enter an auxiliary voltage if you want as well. And a nice feature is it has a lot of ICs from different manufacturers, and you can actually select the one you want, and that'll fill in some parameters like the frequency for you, and maybe your max input or max peak current rating and things like that, so you don't have to even think about that. And also has some user-defined input voltages, the typical ones, the universal, offline, European and North American. Then when you have all those values filled in, you should, if you're lucky, get a list of transformers that could work for that. Then this gives a nice graph of the input current and output currents and a schematic of the winding, and then you can also download a 3D model of the actual transformer as well, and the data sheets, and have a bit more of a detailed look at the transformer to see if it's the one for you. So you have some options. There isn't a massive selection of flybacks or transformers in this at the moment. We're constantly adding to it. So if you're lucky, you'll find something. If not, you'll have to go to the other method, or the easiest way is to contact someone in Würth and ask them for a little bit of help. We have thousands upon thousands of transformers there and there's a good chance you'll find something off the shelf. If not, then myself or one of the other many design engineers can do a custom transformer for you that will for sure do the job. So that's it from me today. I'm a little bit over time, but I think we still have some time for questions, and I'll hand back to Alex. Thanks.
Thank you very much, Thomas. A rough start, but we made it. Let me stop sharing. So let me see, we had some things coming in, but I couldn't follow it because of the shared screen. We have a question from Koen. Let me see. How to simulate the EMC performance of a flyback converter, and what are the things to look out for before taking to your flyback design to the test house? It was asked to Ernest because it was just after your session. Perhaps you can take it this one.
Yeah. So it's a whole new subject, to be honest, Koen. My first answer would be maybe you drop me an email and we can talk. But the whole topic of flyback and EMC, there's a lot of information. So actually, we have custom designs of existing designs that are optimized for EMI, and typically they would contain filters on the input. And for the filter components, Würth is always also a good candidate to go and check out. And then those designs we would provide curves and graphs. They are tested for system performance and stuff like that. So that will typically be the first starting point. How to simulate, I think that is probably also better discussed offline. We have some files that can be used as a basis that were used for specific EMC analysis for flyback generators of, I think, about 1 generation ago. So those can typically be used.
Perfect, thank you very much. And EMC, of course, is always a tricky answer. So yeah, please consult either one of us to help you with this topic. And that goes for everyone else, of course, as well. Thomas, a question for you. You showed at the end of your presentation an equation for the leakage inductance, and there was a number there, 3.194. The question here is, where is that coming from?
That's a very good question. To be honest, I have no idea where it's coming from. But yeah, I think that leakage inductance equation is from some book. I think we just need to look at the ways to reduce it is what I'm interested in, and the 3.14. Yeah, good question, but I'm sorry I don't have an answer. Maybe I can look into it and get back to that customer.
Okay, no problem there. I don't know the answer as well, so I cannot help. Let me see if there are any more questions coming in. Well, at this point, I don't see any questions additional to what we already asked. So that will leave me only to thank you both for this interesting two presentations. Again, we will post this one on our YouTube channel. It will require some editing this time, but that won't be any issue. Let's say within a week it should be online, and then you can review it. And I can imagine that you would also be interested in having a copy of the presentation itself. If that is the case, then please drop me an email and I will send it to you or ask someone to do that. Especially because, of course, there are a lot of equations inside this time, which is always handy to have somewhere near you. Again, thank you very much for attending. Hopefully seeing you next time in one of our other webinars. Ernest, Thomas, thank you for presenting the topics, and well, have a good afternoon. Thank you.